Hello. We're going to talk about general antiderivatives with U substitution in these notes. And before I tell you exactly what that means, let's think about the kind of antiderivatives that we can find as of right now. As of right now, we can find antiderivatives of things in only really a few special kind of cases. We know how to find the antiderivative of something like, say, x squared. We know that because we figured out how to run the power rule backwards. That to run the power rule backwards, you have to bump the exponent up by 1 and then divide by the new exponent. Right, and we can check that. We can take the derivative of that, and sure enough, it's x squared. And then we put our plus c on there to get that idea of the general antiderivative. Could be anything, any x cubed over 3 plus some constant. And we can do that with any power. We can do it with rational exponents, like x to the 1/2, something like that. And then otherwise, we know how to do antiderivatives where we just recognize, for example, the antiderivative of sine x. We think about that for a minute and we say, oh yeah, well, let's see, sine and cosine, those are the derivatives of each other, and the antiderivative of this, the derivative of cosine would be negative sine, so I'd have to put a negative sign in front of that. So we're just sort of recognizing, oh yeah, that's a derivative that we know. The derivative of negative cosine would be sine. We know that the antiderivative of 1 over x, that's a special case, right? We know that, oh yeah, that's the derivative of the natural log function is 1 over x. Right? And we have a few other special cases. Maybe we'll just talk about those real quick because a bad idea to review them. The antiderivative of 1 over 1 minus x squared. It's like, oh yeah, I recognize that. That's the derivative of the sine inverse function. And we also know that if we see something that has a constant multiple like that in the front, we could pull that out to the front like that, and then we say, oh yeah, I recognize that. That's the derivative of the tangent inverse function. Oops, sorry, plus c. And so the point is here that we really only know how to take antiderivatives in a few special cases. Basically, those special cases right now are cases where we recognize an easy way to get back to the original function, either power rule backwards or we just recognize the derivative of something. So U substitution, what this is basically going to allow us to do is to run the chain rule backwards. So I think the best way for me to explain that is to do it with an example. So let's say we wanted to find the antiderivative of this function. So here's an example where you could FOIL this out 4 times and then distribute the x squared through, and you could do it that way. But maybe there's a better way to do this. And the kinds of problems, what we're looking for when we want to be able to do, or when we recognize that we can do this U substitution, is when we have an inside function like this, and we recognize that there's an outside piece here that is maybe somehow the derivative of this. And I'm actually going to change this example. I'm going to, sorry, we can have a little room to squeeze in a 3 there. We'll make this one a little bit more obvious, and then we'll work into ones that are a little bit more difficult after that. So we recognize that this is an example where we can do U substitution, because we spot this inside function here, x cubed plus 1. We think for a second, what would the derivative of x cubed plus 1 be? And then we see, oh, that would be 3x squared. So we recognize that, oh, there would have been something if we were taking a derivative. When using the chain rule, the derivative of what's inside would pop out, right? So this is kind of like the derivative of what's inside. So is there some systematic way that we can kind of repackage that and get back to the antiderivative? And this is how we're going to do it. We're going to look for the what's inside. That will very often be something that's in parentheses, not always. We'll look at some examples where it's not. Here it's pretty obvious what that the inside function is. And then we're going to let u, we'll do a substitution, let u equal that. So we'll let u equal x cubed plus 1. And then we're going to take the derivative of this. Now if this was y equals x cubed plus 1, then we could say dy dx equals this. And here we'll say, since it's u, du dx, right? It's not y, it's u. So du dx is equal to x cubed plus 1. And then inspired by all of the algebra that we know, I'm going to go ahead and multiply the dx up to the other side, like that. There's all sorts of reasons, if you really think about what the du dx is, that these are things that are both approaching 0, that might seem like a little bit of hand-waving there, but we're going to treat this just like it's any other algebraic fraction, and that we can move the dx up to the other side. Okay? And we can talk, there'll be lots of situations we can talk about why this is a good move and why we need to be able to do that. And here, I think we can see that now, oops, when I took the derivative, oh my goodness, look at that. The derivative of this, if you're wondering, the derivative of this, of course, is not x cubed plus 1. It's x squared plus nothing, right? The derivative of this is x squared. Let me fix that. All right, so the derivative du would be equal to x squared dx, right? I'm taking the derivative of this. I'm sorry, I just forgot to take that derivative in that case there. So du is equal to x squared dx, and look at that. It's 3x squared, isn't it? But you're paying attention, you knew that. Okay? And now, let's look back here and see where that gets us. I'm going to try to rewrite this now in terms of u. So let's see what we have. The 3x squared and the dx. 3x squared dx, that's all equal to du. And here on the inside, I have x cubed plus 1 to the 4th. So that's u to the 4th, right? This is the u, times du. So very neatly, this all repackages now according to this u substitution, according to picking the right u, the what's inside here. It all repackages into this. And that's an easy antiderivative to do. The antiderivative of u to the 4th is u to the 5th. Sorry, u to the 5th over 5 plus c, right? That's gone now because we've taken the antiderivative. We've done that. And then we just say, well, what's the u? The u is x cubed plus 1 in there. after resubstituting at the end, because if we're given an original problem with x's in it, we don't want to give the answer. Although this is correct for the answer, it's only correct according to our substitution, so we want to go back to the x's at the end. And I'll leave it to you if you would like to check. I'll leave it to you. I'll leave it to you to check here to see that the derivative of this, if you took the derivative of this and you use the chain rule properly, you will in fact get this as the derivative. Now, if I were you, I would be thinking now, well, that's kind of a, contrived example here because the thing out here happened to be exactly what we needed here. And I'm not going to mislead you here that problems where you can do U substitution do tend to be a little bit contrived in that way, but it does open up another, a whole other world of antiderivatives that we can find. So let me show you a couple other examples that work by this method. So how about sine squared x times cosine x? And it might, as it usually has helped us, it might help here to write sine squared x as sine of x squared times cosine x. And I think that helps us maybe, might inspire us to choose the right u here. The art of doing U substitution is basically the art of recognizing what is the inside function and recognizing that yes, in fact, the derivative of that inside function does show up in some form outside here. So here, there's my inside. So if I say that u is equal to sine x, then du is equal to cosine x dx. Now I skipped this step here. Here I said du dx, and then I moved the dx up to the other side. So here the du, I just put it automatically over here. I'll pause for a second, make sure you're okay with that. And after we've done that, if we've chosen the u correctly, and if this method is going to work, we should now be able to rewrite the original problem in terms of only u. So here, sine of x, that's u squared. And then here, cosine x dx, that's du. So that would be u cubed over 3 plus c. But we don't want to write our answer in terms of u, we want to write it in terms of x's. So u was the sine of x. And that's our answer. And again, I will leave it to you to go ahead and try, if you want to, take the derivative of this and see in fact that it would get you, if you use the chain rule properly here, it will get you back to this. And again, you might say, well, that's, that just happened to be there, just exactly the thing that we needed. Well, that's the way that U substitution works. The kinds of problems that we can do U substitution for are the kinds of problems where, in fact, we do have that piece that we need. But it's not always exactly what we need, so let me show you what that looks like when it's not quite exactly right. Now let's try this. Let's try how about this? Remember, if we were going to try to take the derivative of e to the x squared, it's like the x squared up here is the what's inside. Again, the art of doing U substitution problems excuse me, is that we want to recognize that that what's inside does have some form of its derivative in here. And here you might say, well, the derivative of x squared is 2x, and you only have an x there. But we can deal with that, and that's what we'll deal with in this problem for the first time. So let the u equal x squared, then du would be equal to 2x dx. And the problem here now is that I've got the x dx part, but I don't have the 2. And when the thing that we're missing is just a number, not some we can't import x's that don't exist in the problem. But if it's just a number, then we can go ahead and in the original problem, we can insert a 2 here as long as we balance it by inserting a 1/2 on the outside, because 1/2 times 2, that's just 1. Almost in the same way that when you do, for example, completing the square problems, you add and subtract the same number, or you maybe add the same number to both sides of your equation. So here we're basically adding a 1/2 times 2 because we would like to have a 2 in here. 1/2 times 2, of course, that doesn't change anything, right? And we know with integrals, just like with derivatives, that number can move in and out. That's fine with numbers. So this is still equivalent to the same original problem. Now, this 1/2 still hanging out outside, and on the inside I have e to the u, and now, because I've imported this 2 to the inside, I have 2x dx, that's du. Antiderivative of e to the u is e to the u. Still have my 1/2 out here. And sorry, I want to write the du again, but we're done with that, right? We've taken the antiderivative plus c. And only thing left to do now is I don't want to report my answers with u's in them. I want to report my answers with x's. So that's 1/2 times e to the x squared plus c. And if you want to check, you can check to see that if you use the chain rule properly and you take the derivative of this, you will get that original function that we started with. Okay, so that's how you balance, bring numbers in and out. A couple more examples. How about something like this? This one is a little trickier because there's not an obvious what's inside. So I think we have to think about what our options are here. If u substitution is going to work here, then the u would have to be equal to this, or perhaps 1 over x. So maybe ask you to pause here for a second and think about what the u might possibly be that would work here. So with a little bit of maybe trial and error, I mean, you can always try a u, and if it doesn't work, you could try something else. But if we try making u equal to the natural log of x, and we realize, oh, well, du would be equal to the derivative of natural log is 1 over x. And there's my x on the bottom. There's my 1 over x. There's a 3 there, but that's not a problem. We can move that to the outside. So this looks like it will work. Rewriting now, that gives me, I'm going to go ahead and move the 3 to the outside. I don't need it to be on the inside. And then I get u, right? My u is natural log x. And then 1 over x dx, that's the du. The antiderivative of that is 3 times the antiderivative of u is u squared over 2 plus c. And rewriting again, That gives me, I'll write that as 3/2 times u squared plus c. And I think that looks different enough from this that maybe I'll go ahead and show you. I'll just check this time to make sure. If you want to check your answer, you just take the derivative of this and make sure you get back to the original function. So let's check this one. If I wanted to take the derivative of this, well, the derivative of something squared is 2 times that something to the first power. So I bring the 2 to the outside. 2 times 3/2 is 3, times the thing that's inside, that's natural log x, to the first power, times the derivative of what's inside, would be 1 over x, and that is, in fact, equivalent to that. So that works. This check is a really good idea because remember, we're always going to be a little bit more confident. It's always going to be easier for us to take derivatives than to take antiderivatives. So this ability to check our answers by taking derivatives is a good thing. Okay. And let's see, how about we do one more. How about the sine of the square root of x over the square root of x? This one I think is maybe it's a little easier to spot what's going to have to be the u because it is in parentheses. It is pretty clearly, I think, a what's inside. So I'm going to go ahead and take a leap of faith and say, I think this is going to be the u. If I'm wrong, I can try something else. So let's see, if u is equal to the square root of x, that's x to the 1/2, then du would be equal to 1/2 x to the negative 1/2 dx. Please don't be lazy and forget those. 1/2 x to the negative 1/2 dx. Now, you have to notice here that x to the negative 1/2, that's the same as having the square root of x on the bottom. So in fact, we have chosen well. That is our square root of x that we need on the bottom to go with our dx. Problem is we don't have a 1/2. So I need to import a 1/2 on the inside. And to balance that means I would have to also introduce a 2 on the outside. 2 times 1/2, that's just 1. And now I'm able to, or ready to rewrite. So 2 times the sine of the square root of x, that's u. Du is 1/2 times x to the negative 1/2 times dx. So all of this gets repackaged as du. Then the antiderivative of sine u, sorry, with a 2 out there, is negative 2 cosine u du plus c. And, oh, sorry, I keep writing those du's and dx's on the outside. We don't need that anymore, right? Because we've done this. We've taken the antiderivative, so that's gone. And then negative 2 times the cosine of u is x to the negative 1/2, or sorry, x to the 1/2. I'm going to write that as the square root of x again because that's how it showed up in the original problem. It doesn't really matter. You could write it as x to the 1/2 plus c. And I'll leave that to you if you want to check by taking the derivative of this. If you use the chain rule properly, you will in fact get back to the original function. The original function, of course, doesn't have these, right? But it's equivalent to this. You can check that. And that, my friends, is how you take antiderivatives using U substitution. And maybe I'll just say, as a last word here, to address again the suspicion that you have that these are all very contrived problems where just the thing that you needed happened to show up, right? Well, they are kind of contrived problems, and the truth of the matter is this: you can take derivatives of anything using some combination of the product rule, the chain rule, the quotient rule, the product rule, the power rule, and derivatives of trig functions, derivatives of inverse trig functions, e to the x, natural log, and so on. Using some combination of those rules, you can take the derivative of anything. Taking the antiderivative is a much, much more difficult problem. And I'm not saying it's more difficult just in the sense of it's more difficult for first-year calculus students. It's by its very nature, it's a more difficult problem for everyone who's ever attempted to deal with this. So here, these contrived problems, they are contrived, but at least it's more things that we can find antiderivatives of than we could before we knew about this technique. One way of understanding what's happening here is taking derivatives is what is sometimes called a one-way process. Much in the same way, for example, if you imagine taking a gallon of white paint, and if you were painting something and maybe you wanted it not to be not white, you could add some pigment into that white paint, and you could mix it up, and maybe you could have some blue paint, depending on what pigment you add. Well, that's fine, right? It's very easy to do that. You add some pigment in, you mix up the can, and you've got blue paint. But that's kind of a one-way process. Once you've got the blue paint, it's much harder, maybe almost impossible, to undo that. If you want to take the blue paint and extract the blue pigment that you've mixed in and just get the original things, the blue pigment and the white paint, that is really, really difficult to do. There might be a lab somewhere where if you have, I don't know, $100,000 or something like that, you could invest that money in a process that would extract all of the blue pigment out of the white paint. But it's a much, much more difficult process than it was to just mix it in. So taking derivatives is kind of like this. It's really easy to take a derivative. It's much harder to undo that process. And in fact, there are lots of functions out there in the wide world of functions where you cannot find the antiderivative. These are examples, contrived as they might be, where you can. But in general, I could just make up some messy-looking function, and you could say, hey, smart calculus teacher guy, what's the antiderivative of that? And it's just not something that we can know. It's not something that we can have a closed form of, because this particular method doesn't work, and any other method that we know of, some of which we'll learn later in this class, some of which you might learn in a more advanced calculus class like Calc 3, none of those methods work. So sometimes we just have a function where we cannot find the antiderivative. And that's just the way it is. It's kind of a one-way process. Derivatives, easy. Antiderivatives, hard. What we can do, though, is we can, with the aid of technology, our graphing calculators, computers, we can look at what an antiderivative would look like. Even if we can't find it, we can, through the process of area approximation, we can get a real good look at what an antiderivative would look like, even if we can't find an actual closed form, nice answer to that problem. So we're stuck in that situation right now, and we have to deal with that. So again, if these seem to be kind of contrived, they are, but that plays, at least I think, to our favor, that the contrived nature of them leads us toward being able to spot what that U needs to be in each case. It makes it a little easier for us. So there you go.